All right, ladies and gentlemen, hello and welcome back to the only nationally syndicated show all about the information economy. It's called Inside Analysis. Yours truly, Eric Kavanaugh. And I'm very excited to be talking about one of the hottest topics out there. Who doesn't love a fun race car? Who doesn't love a software defined vehicle? What is that? What is a software defined vehicle? We're going to find out on the show today with a couple of experts. We've got Michael Franz from FPT calling in, and also Florian Rohde, who is with a company called iProcess. He used to work at Tesla, so he's done some cool stuff. He's out there in Las Vegas, so you know he's having fun. I mean, when you live in Vegas, I mean, come on, it's 24/7 fun all the time. So we're going to talk about what's happening in the world of vehicles, and I think this is fascinating. I'm an old timer, so I had cars where you had to roll up the windows. You know, there's something special about that. If the fuse breaks, you could still roll the window down, so that's nice. But other than that, we like to have automatic windows and automatic, gosh darn everything these days. I mean, the amount of innovation in this space is really quite remarkable. And obviously, Elon Musk had something to do with that. Not everything, but he had something to do with it. And our guests are going to help us understand what is going on out there. So maybe, Florian, I'll start with you. Tell us a bit about yourself and your company and how you got all into software-defined vehicles.
Yeah, thank you, Eric. And you got that right with Vegas. It's 24/7 fun. Um,
All the time.
I've been in the automotive world for about 20 years now, and the most interesting window of that started in 2012 when I joined a small company called Tesla Motors. And it was a very small, it was about 2,000 people in the world. And we started building those cars. We never called them SDVs or software-defined vehicles. We just decided, let's build a car the way we think a car should be from here on forward. And it turns out then at one point the industry labeled that SDVs. So I was at that company for 6 years almost, and I was responsible for all the validation, so the testing of the software before it goes out of the development into the hands of the end customers. And we signed off over 700 software releases in this
Wow.
6 years. So it's a huge amount of software we got out. And yes, let me just pick up real quick with your window lifters because electric windows are not SDV features. Just to take that out of the way, those are EE features. That's the
That's
last
funny.
generation of cars. Some were started in the early 80s, and we see that currently still out there. So those are actuated systems, and they're controlled by microprocessors. SDVs go one step further, where you actually have a feature-rich, updatable, and upgradable vehicle that is continuously improving. At least so is the plan for the future from here on.
Yeah, that's really interesting stuff. And you can adjust any number of things in that operating system, right? Because it's got a computer. I mean, lots of cars have had computers for a number of years, but not a very sophisticated computer. And this one is even more sophisticated than any of the ones that have come before it. Can you kind of walk us through what goes in there? What kinds of things can you update? Is it how the car is running? I mean, are you actually affecting fuel, oxygen levels or something? Get into the details for us.
So the cool thing is you actually already talk about the next generation of SDV. So what we see currently is that you actually have the controllers, the computers in the car working together. This is the first generation of an SDV. So you still have distributed computers in the car. It's not only one, but they are starting to work on things together. So you have features and functionalities that are provided by several computers in together. And I have a very simple example from my Tesla times when they came out with a feature that you can use your microphone from your Bluetooth speaker set
Hmm.
to talk to the people outside of the car through the pedestrian speaker, warning speaker. So
That's
those
funny.
systems were never designed to work together, and those systems were never interconnected with each other. But with software-defined vehicle functionality, they were actually able to make them work together. If that feature is really necessary or not is a different question. But they make them work together and provided an over-the-air software update, similar to what you know from your cell phone, into the car to offer you that new feature. The next generation will be what we call HPC, so high performance computers, which you can basically assume there's like a central computer there's some logistics in the car that it's probably gonna be more like two, one in the front and one in the rear of the car because of the harness and the wiring issues. But in general, that will be the next thing. And you can, in very, very simplified ways, you can think about your 486 IBM computer where you had to put all those stuff together that it works to your laptop you're probably looking into right now that is out of the box, and you have shared memory between the graphics driver and the hard drive and the processor and this kind of stuff. So that is in a very simplified way where we are going.
Yeah, and a lot of the features do revolve around safety, right? Like on keeping you in your lanes, alerting you, doing things of this nature. And I think there's been a lot of advancement in the last few years of identifying what is a bicycle nearby, what's a car coming at me, what are these things? Because obviously the car has to identify this and then act in real time. You can't be, can't wait for an overnight update when something's coming at you, right?
Yeah, and one of the reasons is because the compute power in cars is growing significantly. So the features you just mentioned, they need a lot of compute power in order to do the vision and the perception, and then the reaction based on that. And we see this catching up in cars. You have seen much higher compute power already in like domestic applications like computers and so on. But cars is a little different beast because they can be outside at minus 40 degrees Celsius. And it can
Right.
be outside at here in Vegas. We topped out at 47 degrees Celsius, 117 Fahrenheit, I believe. So your cell phone will not work in either of those conditions. So this is why the car industry is a little behind, and this is maybe where Mike can chip in a little bit from, pun intended, from the chip side of things,
Ah.
because it takes a little bit longer to make those high performance compute chips ready for those environments cars are used in.
Yeah, that's a good point. I did some work with the Electric Racing Association over in
Mm.
Europe a couple years ago. It was a lot of fun. I mean, those electric cars are super fast, and the
Yeah.
young kid, the driver, who is such a neat guy, he gave me the headline for the article. He said, "We have all the torque all the time." I was like, "Oh, that's the headline right there." And he is
That's the
such a
headline right there.
wonderful man.
Nice.
And but I learned that there was a race in Spain somewhere where they had to cancel it because it was too darn hot and the vehicles just wouldn't run. So I'll throw it over
Mhm.
to Michael. The real world can be brutal out there from heat to cold. I mean, you're in near the
Oh yeah.
Detroit area, so
I'm
you know
I'm
about
in I'm in
cold.
Michigan, so yeah, we're currently about to start going through some things. And yeah, Eric, you're right. The vehicle environment is not monolithic. It's not in an air-conditioned environment 98% of the time. We have varying applications and conditions that the vehicles we know and love have to operate in. That's why for years manufacturers have tested in Arctic conditions. They've tested in desert conditions. Because they have to make sure that the integrity of the vehicle and everything that's in it can operate in a multitude of environments before it goes on the road. It's not good enough to launch it with an application and say, okay, we'll worry about that feature or feature set in the next update in the next after 90 days. It's difficult to operate in those environments like that, and of course, that's where the ideation meets the reality. Oftentimes in the automotive industry,
Right.
where you can market and position a product or a brand in a certain way, and then the regulators have to come in and say, well, guys, this is actually what you've got, and this is why we classify it as X, Y, or Z, right? And that's important because at the end of the day, it's still a 3-ton weapon if
You're
it's in
right.
the wrong hands,
Right.
and needs to operate in a very safe condition. And of course, the more we expose vehicles to software, the more we have to secure them. Because this becomes the next problem, because as you open and expose yourself to the technology, so you open
Sure.
and expose your product and your service to bad actors around the planet. And again, not all vehicles are created equal, right? And never will be. There will be manufacturers who will launch software-defined vehicle technologies that are not as secure as everybody else's. And I'll give you a classic example, right? From way back, the Volvo passenger car brand. When I say Volvo, most people think of safety, and it would take an extraordinary amount of money for any other OEM to ever go and climb that mountain and say we're safer than a Volvo. That people just don't do it. It's the same around software development, right? The manufacturers that and this is my personal belief, the manufacturers that take care of the security and the securitization of their product as they launch their feature sets and software will ultimately win the race, because we will unfortunately see some things happen as this technology matures and goes into the industry, right?
Well, and that is, I mean, you bring up an excellent point because, and I often sit and think about this stuff, security and protocols and
Yep.
technologies. And of course, the key fob comes along, and that's great because you can find your car in a parking lot. But if you lose your key fob, so can the bad guy. Right? You can just
Yes.
grab your key
Yes.
fob and walk around the parking lot going beep, beep, up there it is. I'll go steal that car.
Well, we all know the nightmare stories already of things like key fobs that are not secured in the security code hopping, where bad actors can jam those signals, copy them, and then open your vehicle and drive. Right. This is not new. This has been in the industry for many years. And it's the simplest function today. Click the button, open the vehicle, right? Or lock the vehicle, and proximity to the vehicle for auto unlock. All of
Right.
those things already present a risk, and that's known technology, right? So we have to take care of all of these things in a responsible way, and we have to take care of it in a multitude of places and times and locations and geographies and technology stacks and things like mobile networks that run on different frequencies. The vehicles have to talk on multiple frequencies in different geolocations
Right.
to the back end and from the back end to itself. So it's a complex world. And we have and manufacturers and the tier one partners have a responsibility to look after the vehicles that are already on the road for a number of years, and they have
Right.
to play for
That's
the
right.
future at the same
Yeah.
time. So it's a huge responsibility, I think.
Yeah, that's a really good point because you do have this entire arc of legacy vehicles out there. I mean,
Oh
you've
yeah.
got
Oh
cars
yeah.
from the 1940s still driving around. So
Right.
you have to
And
keep all that in mind.
the reality on the road is today in America, the average vehicle is 12 point something years old.
Wow.
People are keeping their cars longer and longer because affordability is an issue. The economic climate's an issue, right? We have to acknowledge these things. We must push forward, but the reality on the ground is that the vehicles we even introduce today are probably going to be around for more than 10 years, and somebody has to take care of all of that technology stack as it goes forward. In IT, we talk about technical debt. In terms of aging infrastructure and aging technologies, I believe that the industry will needs to take care of the when you say technical debt of today's vehicles 12 years from now, because the vehicle in 12 years from now will look very different to what it is today.
Well, and
So
that's
I
actually
would,
oh, go ahead. Yeah, go
sorry,
ahead.
yeah, I would argue I'm more afraid of the vehicles of last year than I'm afraid of the vehicles from 13 years ago from security point of view, because
Oh, absolutely. That's why my car that I own, not lease, is 10 years, right?
yes, so it's as soon as the vehicles start to become a member and a participant at the communication that goes around, like we call this V2X or vehicle to
Yes.
everything or vehicle to vehicle, V2V. This is where security actually has to go a whole level up, because my vehicle can now tell Mike's vehicle to slam the brakes for a variety of reasons. And if I have a malicious attack planned on Mike, I can just tell his car to stop. Obviously, this is a very simplified example, and it is not that easy. But there are those things, and it is the fact that this technology is out there, as Mike mentioned, and it's available not only for car makers, it's also available for people who have bad ideas around cars.
Right.
So I would even argue they are ahead from the technology point of view compared to the car makers and OEMs right now from security point of view.
Wow, that's interesting. And you reminded me of something that I think is quite fascinating because these cars are instrumented, and so you're gathering data from various points like the brake and the engine and other places like that. I'm guessing that is incredibly valuable data for the next generation of car design, right? For being able to
Oh
optimize
yeah.
the wheels or the drivetrain or whatever the case may be, having that just massive treasure trove of data coming in from the vehicles, that's got to be fun to work with, right?
Yeah, so the fact is that as an engineer, you only know that if you under-designed your product. If you over-designed it, you never know because it will never come back to you, right? So they come back to
That's
service
right.
when something breaks. But if they never come back to
Funny.
service, you don't know if you reached 99% of the capability over lifetime or 1%. And 1% is a nightmare because that means you completely overpaid the development of that product.
Hmm.
And we had at Tesla, we had those situations where we actually looked at the data and we actively took that information into consideration for cost downs and for next generation vehicles to not only make those things that broke more sturdy and better for the next generation, but also make those things that were completely over-designed and therefore also probably too heavy, more lightweight and better suited for electric vehicles. But I have to say as well, depends on where you are in the world. There's huge discussions who owns that data. Is it the owner of the car who creates that data by driving the car? Is it the maker of the car who, collects the data in your car? Is it maybe a mixture of that? So that has not concluded yet, that discussion.
And Florian is being a great engineer by saying he wants to collect all the data all the time.
Of course.
And of course, I always counter that by saying, and right now, because we're building it out and we're discovering new things, the engineers are driving that push for data. How much of that data is really needed when the vehicle is launched, right? At what point do we have to say, well, not everything needs to be available real time live. Certain things have to be. Other things can maybe stored and uploaded later, because at the moment the amount of data is exponentially 10xing. The more technology you put in the vehicles, and the more it's algorithm based in terms of what the performance of the vehicle, etc.
And there's a very simple example, because the car communicates the exterior temperature with 100 hertz. Inside the car, but you don't have changes in the temperature within milliseconds, so you don't really have to collect that data on a 10 millisecond base, right? Every 10 minutes is enough. That's a very simple example everybody can grasp.
Right. No, that's a good point. And we're coming up on the end of this first segment here in just a minute, but what I think is really fascinating is the whole design process and how all these different parts have to come together. And so you talk about something having been over-engineered, or it's too heavy, or it was too expensive. These days we're getting to the point where you really can map out and understand how much time it took to build this part or that part, what the parts cost themselves. My point is, like, we're so much better today than we were probably even 20 years ago in terms of being able to really understand what is the total cost of ownership, what is the cost of all the personnel who went into the design phase to get us to this next stage, and how do you prioritize? That's what I'd love to understand is, as you roll out one car, the 2025 version, I'm sure immediately the engineers are already thinking of the 2026 version. What should we change for that? Do people want more? Do they want better gas mileage? Do they want better comfort? And then knowing like how to compartmentalize all that stuff, that's got to be a fascinating series of meetings and discussions and decisions that are made to determine. You have to hit certain deadlines and, okay, this is what it's going to be for next time. Well, folks, don't touch that down. We'll be right back with a fantastic conversation about software-defined vehicles. You're listening to Inside Analysis. All right, folks, back here on Inside Analysis, talking all things software-defined vehicles. We've got Michael Franz on the line from FPT and Florian Rohde from iProcess, and we were just chit-chatting about what goes into all this. The decision-making process and decoupling came up as a key topic to dive into. So I'll throw it over to Florian first. When you say decoupling software from hardware, what do you mean by that?
So originally cars were designed mechanical, electrical, and software, and this all came together to what we call SOP, the start of production. And then you basically deliver that car to, the dealerships. They start selling that for a couple of years, and you and your engineering team in all those three branches start over for the next generation and continue. Especially at Tesla, we started this decoupling completely. So the new vehicles are inheriting the software of the other vehicles. So basically what you see out there in Tesla is one software platform that, okay, it's a little bit of configuration is different per car, but in general, there's one software platform that runs on all their cars. So it's decoupled from the actual version of the car. So a Model S and a Model 3 is technically the same software with certain varieties in there. And so like this, when your car gets into a next generation from mechanical point of view, your software is actually not waiting those 4 years for that. It's continuously evolving and is then applied to new platforms that are going out. So and therefore, it's the software and the hardware is decoupled from each other.
That's cool.
Right. And Eric, just to layer on top of that, we used to have in this industry an 8 to 10 year window of a vehicle, and around about 4 or 5 years you get a midlife cycle impulse or a midlife cycle update, where the manufacturer would change the front bumpers, they change the lights a little bit on the outside. You may get a couple of more paint configurations, maybe 1 or 2 more interiors, and then sort of the last year or two of that vehicle you get the full house, right? The manufacturer would throw the full Monty at it. All the options you were paying for before are now built in, because now they want to move the metal. And you suddenly get the best wheels and tire packages, you get the best engines, and off it goes, and they ride that vehicle into the sunset, because in the background, over the last 8 to 10 years, the engineering and design teams have been working on the new version, right? And suddenly you get to the current situation in the market right now, where the pressure's on, and the OEMs have all turned around inside themselves, trying to figure out, how do we get to release a vehicle in 18 months from scratch, from a blank piece of paper? Because manufacturers in China are doing it. How are they doing it? How is this possible? And what Florian talks about in terms of decoupling a software stack is exactly that. They use the same software platform. It's almost like using a software platform to build a home appliance, and you can generate 4 or 5 brands, all looking different, but they're all doing essentially the same thing. This is the way that the industry is moving, and this is causing pressure in the market, because in the industry, because the need is accelerating to launch new product faster and faster at lower cost. And based only on the fact that you can redesign the shell of the vehicle, basically, and some of the underpinnings and the performance, but the software driving that vehicle is actually similar, very similar, 98% copy and paste.
Yeah, that's very cool stuff, and I'm guessing that you've got some good digital twin software out there, right? To design the new cars and to kind of test them in a
Yeah.
virtual world and see what happens, right?
Well,
So
now you're opening another can of worms. Yeah, go ahead for it.
well, the term digital twin is used for actually a variety of things, right? So there's no one digital twin. So some people hear that and they say, "Oh, this is just like a simulated car. You can just like see it through 3D, glasses or something like this." But there's a variety of digital twins. There's much more simpler ways out there, where you just have certain models or certain algorithms and you test them, all the way up to like packaging digital twins, where you figure out, can that seat move enough to the back without hitting the knees of the person behind you. Those are very different digital twins, so they're very purpose built. And the short answer to your question is yes, there's a lot of software simulated parts or versions of that vehicle. And to go back to some anecdotes, I remember it was a long time ago, some 10 years ago, I saw Elon Musk with some Oculus Rift thingy handing around in the air, and so he was checking out the Model X design in a virtual environment that we couldn't see, because he was just sitting in the middle of the office and waving his arms around. So it was hilarious. But this is where we are going, right? So the design and the packaging and all that stuff, that is going all virtual before it goes in. Crash testing. We did crash testing 99% in simulation. The first Model 3, I believe, that crashed was at the crash test facility for the actual certification. So we didn't crash any of those before. And it was spot on with the simulations. So in software, we're actually doing this as well now. So we have software environments. Virtual ECUs is one of the buzzwords this year in the industry, where you can test your software without the hardware, and this is where it's getting really important, you integrate it with other pieces of software and with other pieces of the car, because this is where we see the most challenges. It's getting more complex, it's getting more fun and interesting, but integration is the large challenge we are all facing. So simulation is helping us a lot there.
Yeah.
I'll give you another idea, Eric. Driver monitoring, right? There's a legislative push to get driver monitoring more and more into vehicles going forward. This is camera tech watching your eyes, and the camera can tell when you're getting drowsy based on certain tell points better than your life partner sitting in the seat next door to you, right? They're watching the speed of how you're blinking your eyes, how long your eyes are closed in a blink, and that's triggering the warning signals to pull over and stop the vehicle, right?
Wow.
Now, in order for that to get tested, it would take hundreds of thousands of hours of a guy or a girl behind the wheel of a car driving around until they're literally starting to pass out. Simulating that monitoring is a deal breaker in terms of getting that technology to get passed and implemented safely into vehicles. And it's a crash critical component, right? You need to be able to have this, and I think it's a fantastic idea that the driver monitoring is not to monitor you and what you're doing; it's to monitor that you're not falling asleep behind the wheel. And if we have the capability to do that, then I believe those are features and functions that are great to have.
Well, and it
Really
is
important.
great. It's like when I go to the airport, sometimes I get annoyed by going through all the security stuff, but it's
Hmm.
like the argument is, hey, if we catch one person who was trying to do something bad, it's worth all the effort. It's the same in the car industry because
Right.
let's face it, man, like you said, it's a 3,000 pound weapon if it's
Yeah.
not managed properly. And so
Yeah.
that's why these safety features are so valuable and so important. And that's good stuff because, people they push the envelope. I've been there myself.
Oh
I've
yeah.
driven longer than I should have when I started getting
Yep.
tired trying to make some hay, while the sun is shining. And
Of
if you
course.
get that little warning, ding, 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 it's like, okay, I do need to pull over. That's when the wife's like, I told you, let's pull over.
Yeah.
Eric, I
I
have
think it's
to
going to
one
go
second,
even
Mike.
more. Yeah. Go ahead,
Yeah.
Vic.
Eric, I have to give you a quick dose of reality. Our cars are not 2-3,000 pounds. They are
Oh, no.
double that.
Oh, wow.
They're getting heavier and heavier because of the
Yeah,
batteries, right?
yeah.
But Eric, I think it's going to go further than just the coffee cup on the dashboard, right? That's where it started. Time to take a break because it's timing how long you've actually been running in the vehicle.
Right.
It's gonna get to a point where the vehicle's gonna
Take
literally pull
over.
you aside
Yeah.
and into a safety zone and switch off, right? No, because people ignore the safety sign,
Right.
right? I mean,
That's
we
funny.
have maximum speed limit signs all over the place. And do people listen to it? No, they don't. They look at it, they don't accept it, they just do whatever they want to do. So so
It's funny.
so I think it's important, and I think it must be pervasive in the industry, that type of solutioning, especially heavy duty trucks. We move 70% of our freight by road in North America.
Wow.
We need to really think about those kinds of things and say, hey, Mr. Driver, I know that you're allowed X number of hours per week or per month on the road, but actually on this specific trip, you are actually starting to doze off. Let's get you safely pulled to the side, so we can sort that out. And I think
Yeah.
that kind of tech I love, right?
Yeah. Well, and it's like I've been fascinated just in my own life noticing what algorithms can notice about you, like your behavioral patterns. People don't realize how transparent they are, frankly, but a machine is just monitoring behavioral patterns, and those patterns of getting drowsy are pretty significant and pretty clear. And so it's wonderful. I mean, you can't really calculate how many lives are saved, but you know for sure that lives are being saved, right?
And
Exactly.
it's not only that, right? It's also there's a medical emergency, for example. We're not only assuming that people doze away behind the wheel, but there's
Yeah, yeah,
also people have
absolutely.
medical emergencies. And
Yes.
just to close the loop, I think this is a great example of SDV as well, because you have a camera feature that detects that there's something wrong with the driver. It
Mhm.
then hands over that information to the autonomous driving feature set of the car, which then,
Yes.
together with the map system and with the cameras outside of the car, safely pulls that car over and
Wow.
starts an e-call to bring you the medical service you need. So this
Right.
is it's a simple but good example how things work together, even though they are separate parts of the car.
Yeah,
Yeah.
that's an excellent point because people do have a cardiac arrest or a stroke. I
Yeah.
mean, a
Oh
number of
yeah.
things can
Yeah.
happen. And if your vehicle can then take over and understand what's happening, move you to the side, get you so you're not going to harm yourself or someone else, and then of
Exactly.
course call call the paramedics to come get you. I mean, that is a wonderful confluence of technologies to help preserve people, lives, and of course the car too, right? Because if someone falls
Right.
asleep behind the wheel, man, whoo, it goes
Yeah.
bad
It's
real
trouble.
fast. Yeah, it
Yeah,
goes bad real
exactly.
fast.
Yeah, if you're doing 80 miles an hour down a Tennessee highway and that happens, there could be some trouble, right?
Oh yeah. Well, and just the other day we're driving back. In fact, last night I was driving and you hit the bump brrr, like that, and my daughter's like,
Hmm.
"Why is it doing that?" I said, "Because it's warning you if you're
Yes.
going around a curve and you don't want to
Yes.
be in the oncoming lane around a blind." I was very proud of myself when my daughter picked up what a blind curve is. I was like,
Yes. Great
So
job, Dad.
this is a very analog feature you encountered there, but we're working on the digital version of that.
That's funny. Yes. It's a very analog feature. And, blind turns, I mean, all it takes is one accident when you're younger to really
Yeah.
appreciate the significance of an accident, of a car accident. And I'm
Mhm.
I'm the kind of guy when I'm driving, I'm always thinking, and then there's a blind turn, like, be careful, man, because you never know. Someone could be losing control. There could be an ice patch or something. And, if you're in a small car like my Miata and some dump
Oh,
truck comes
nice.
around that corner, man, let me tell you, it's going to
But
be
this
unpleasant.
brings us back to what I said earlier, the vehicle-to-vehicle communication. So if you have those blind turns right in the car in front of you, encounter the ice patch, it will actually tell your car, not your
That's
Miata, but
crazy.
your
Your
connected
other
car
car.
will get
Yeah,
that
your other vehicle.
information, right?
Yeah.
That's this is a good topic to dive into. How far along are we in that vehicle to vehicle communication? So if you have two new Teslas, for example, what you're saying is that and how do they sense? Is it a sort of a GPS driven thing that knows, okay, you're now
Yeah.
in my vicinity and you're coming around a turn? Like, can all those factors actually get processed in real time to trigger a warning like that?
Yeah, so first, I think we are already at a very good point within a certain brand. So Tesla to Tesla, I think, is much more evolved than Volkswagen to BMW or something like this, because they are still working on also on some standards because they have to speak the same language, so to
Sure.
say, right? But in general, yes, you're correct. So there's something we call geofencing. So they know which area they are, and they're basically similar to a cell phone. They just book into, look, I'm in this area now. I'm driving through San Francisco. And then it's actually called CV2X, so cellular vehicle to everything. So this is when the cars use the cell network to go basically through a satellite or through, I mean, not an actual satellite up there, so through a server and talk to the other car. The other thing we will see within the next few years is how they talk to the infrastructure. So the red light communicates the status of a red light to your car. That can reduce your consumption because your car will actually, on autopilot, will slow down earlier and come to a stop without wasting energy, stuff like this. So this is happening in controlled environments and in smaller patches already. Over the next 5 to 10 years, we will see that rolling out really in a way that everybody realizes it. And there's a simple add-on on that. So I have a friend who runs a company who works to get green lights for emergency vehicles. And I said, wow, but you would have to get every light online. This will take you 100 years. And he said, no, actually, where you live in Las Vegas, more than 90% of the traffic lights are online already.
Or synchronized already, yeah.
Yeah, so we don't know because we don't focus on that technology, right?
Yeah.
But a lot of environmental technology is already ready for all of this stuff we're talking about. So it's getting there. It's about to get it all together.
I'll give you another example, Eric. There's currently a rollout of a program for emergency services to notify certain brands of vehicles that they are in proximity of an emergency vehicle. It's coming up behind you, or to your left, or to your right, or in front of you, based on your orientation of the vehicle.
That's crazy.
That kind of technology, I believe, is really a great example of using that cellular down to single cell information. And repeating it across even a different brand. I mean, it'll be a fire truck telling whatever product that's coming. As soon as that becomes pervasive, that type of thing is great because it starts to clear the emergency lane, make the vehicles pull over the way they should pull over. You're not looking around rubbernecking to figure out where's the fire truck or the ambulance, because nobody can ever tell. But it's behind you and it's approaching, right? So that's a simple example of that vehicle to X, that vehicle to anything environment, and how that is going to start becoming more and more pervasive as it goes along. Of course, it's very difficult to get things like the built environment to talk to the vehicles. A simple example is who owns the traffic light and the data coming in and out of the traffic light,
Yeah. We'll pick this up out of the break, folks. Don't touch that dial. You're listening to Inside Analysis. All right, folks, back here on Inside Analysis, talking to a couple experts in software-defined vehicles. Such cool stuff out there, and I'll throw it over maybe to Michael first and then to Florian. I remember learning this ultimate sales pitch for self-driving cars, and that is no more traffic jams, right? Because if you can orchestrate if you can orchestrate every vehicle in this environment, you won't have the darn traffic jams anymore. I mean, you can at least expedite traffic at high peak times to get through difficult periods of time, because who likes a traffic jam? Nobody likes a traffic jam. Nobody. I can't live in traffic jams. I lose my mind in a traffic jam. I will pull over and do something else for an hour to not have to sit there in a traffic jam. But go ahead. What do you think, Michael?
And you're going to continue pulling over to do something else
Yeah.
while you experience the traffic jam for probably as long as you and I still have a valid driver's license.
That's funny.
And the reason for that is because it's the simple law of physics, right? Two solid objects cannot occupy the same space at the same time,
That's right.
regardless of the algorithm. Right.
That's funny.
The bottom line is we are still working 8 to 5 as we were in the industrial age, when we are way past the information age. And this is the reality that we have all signed up for, right? So if you're in Washington and you have in DC and you have to do that run in that side of the world, if you're in Dallas Fort Worth, you have to do those runs. Atlanta, it's not going to change because everybody's still on the road, right? We may smooth out the edges. We may shave a couple of minutes, but the bottom line is everybody's going to knock off work at 5 and head home and try and be home by 6:30, and that means that 1 million people need to be on the road at the same time,
That's
right?
right.
And hopefully we have less accidents, which means the lanes stay open, which means it's a bit smoother. And hopefully we come to our senses as a society and go, in the information age, do we really all have to knock off at the same time? Can we maybe think a little differently about the world we live
Right.
in? But that's another story for another day. But yeah, the bottom line is, and if you've ever been to a city like Bangalore or Delhi, you know that there's no way that a fully autonomous vehicle is going to solve any traffic problems in that part of the world in any time soon, right? So that's
That's
the
funny.
way it is, right?
I got a little bit of a ray of sunlight for you here, Eric. So it's
Go for it, but
so
give
first,
him the sales pitch.
yeah. So actually, I'll just pick up what Mike said. So there are a couple of different reasons why you have a traffic jam, right? So one of them is congestion due to a high frequency, a high number of vehicles at the same time. There, actually, yes, Mike's right. You can't occupy the same space with more than one vehicle, but we can reduce the space between vehicles. So that makes that a little better. We call it platooning, for example. So you have the vehicles communicating with each other. That takes out the need for the distance in between them, and you can have the basically like pearls on a string. Then the other thing, which is I think is much more important, is accidents as a cause of a traffic jam, and that is our all common goal, to reduce the accidents to a minimum by applying those features and functionalities in software and in the vehicles. And like, I don't know the percentage of traffic jams caused by accidents versus congestion, but I know that traffic jams caused by accident in combination with congestion are the worst. So we try our best to get really the safety, and that's the number one on the sales pitch, right? It's safety, then it's comfort, and then it's all the other stuff. And like that, we reduce your problems with traffic jams, hopefully, by reducing the number of accidents on the road.
No, that makes sense. That's good stuff. And you're right that when you get an accident and you have congestion and all these things at once, and it's snowing outside or something, that's when it all kind of falls apart there. I'm curious to know, Google and of course, what is it, Waze and some of these other apps are getting very good at being able to sense how many cars are in a certain
Oh
area. You
yeah.
get these warnings on your phone. How much of that factors into what you guys work on? Are you able to tap into their system and understand how they do that? I know you talked about standards and protocols and things, but where are we in terms of really sharing that information, even in real time at scale?
I think traffic, we are like there. So sharing
Yeah,
traffic
we're there.
information, you can have that down to the granularity of a couple of meters. Other topics is a little trickier, but there's also sometimes there's contractual reasons. There is
Sure.
the non-disclosure agreements and so on. But on the traffic side of things, I think we're spot on. It's available to you as an individual. It's the same available to your computer in your car, so they can do intelligent route planning. They can do intelligent charge planning if you choose to go electric. They can take all this into consideration. So I think that's a great example of how collaboration should work, and it should actually work in other areas soon as well. But traffic, spot on, already working.
I think the next generation overlay is really what we call precise positioning, right, in traffic. So at the moment, your mapping technology that you use, probably Apple CarPlay or Android or Waze or whatever you're using, is telling you that you're driving down Main Street going north, right, versus south. It's not telling you you're in lane 2 or 3 on Main
Right.
Street, and lane 2 means you must go straight, right? So
Right.
precise position is really getting that vehicle to say, I can get you within centimeters or millimeters or less than an inch of where you actually are as a vehicle in those lanes, because
Wow.
that starts to help you the vehicle understand when the autonomous drive system or the assisted driving system says turn right, it knows you have to be in the right lane of 3, and if you are not in the right lane of 3, and a practical example, sometimes you're driving down the road and you get a glitch and the car thinks you're at the McDonald's parking lot and you're not at the
Right.
intersection, right?
I've seen this.
That
Yeah.
is not precise position. Precise position means it's got to know you're there, right? And that can be done with a myriad of ways. It can be done by satellite, precise position overlay of the cell network. It can be done by camera and lidar sensing technologies based on other vehicles around you in proximity to put you in the correct lane.
Wow.
And probably it'll be a combination of all of that stuff as it goes forward. But that for me would be the next generation of precise position. So and
Yeah.
then it starts to help things like traffic congestion, because then the built environment says, oh, hang on, Eric has got 55 guys and girls behind him in the right lane, all trying to get into the stadium to watch the game. Let's open that turn right signal 55 seconds longer per go, so we can start to alleviate that queue, right? Then we're starting to talk about smart systems, live on the go, algorithmic based solutioning, right?
I love that. I can't wait for that finally the traffic lights are not just green for empty. You know, I have like literally
Right.
like I'm waiting at a red
Right.
light and there's tumbleweed coming through and it's like, why, right? But the good news, Eric, here is everything that Mike was talking about is actually ready to go. So we see that rolling out already. So this is actually the state of the art on the R&D side of things. We are seeing this coming out with new generation cars. The traffic light shifting in or changing in my favor. I haven't seen that yet, but I'd like to see that soon.
We can pray about
Yes, but it's a good snapshot of where the technology
what's
is
possible.
already.
Yeah, what's possible, right? Yeah, and Eric, the precise position, I'll give you another sort of example of where it's working in the agriculture sector. So autonomous vehicles in agriculture is already pervasive. It needs to be, because we need people to do work in large areas at the same time, right? And when you're spraying crops with insecticides or with chemical enhancements, whatever you have to do on a farm, I don't know. There are legislative requirements around where you must stop and start the spraying of those crops, and those are defined geographically as a very precise line. And when you use precise positioning, you can actually dictate where that spray actually starts and stops autonomously already, because the vehicle can be tracked to that level, because they can map those areas very well. So it's just to give you an idea of how that technology can really overlay right into adjacent industries.
Well, that's good stuff. And then, urban planning, for example, understanding. I remember I interviewed a guy in the earliest days of my career who worked for the Illinois Department of Transportation. And he told me a couple of interesting things. He said, one is when you plan to build new highways, you cannot project out the new traffic you'll expect to get based upon this new highway. You have to build, at least back then, you had to base it upon current traffic patterns. And so there's a
Right.
lot of effort that goes into that. And getting back to the data side of things, we got about a minute and a half left here. All this data is very useful. I mean, for like potholes, for example. Do you guys see that program with Domino's Pizza where they're like, call in, tell us where the pothole is, and we'll fix it for you? I was like, that's brilliant.
Yeah, even though I don't think the cities have the problem that they have people sitting around not knowing what to do and waiting for somebody calling in for a pothole. But I'd like to jump on that real quick with a 20-second thing about AI, because we haven't really talked about AI, but this is where AI starts to shine a lot in our industry, because we gather so much data and there's different approaches on AIs. It's the server-based AI, which we call a data lake. You just dump all that data in there and you let the artificial intelligence go through and understand what do we learn out of all this data. And then the other thing is what we have not seen yet, but we will see soon, is what is called edge AI. So edge AI means there's AI actively learning in your car. and
Mhm.
it starts to make improvements to the behavior. So this is probably a complete different or additional segment of an hour. So I will stop right here. But as you can hear, we can talk about that for.
Invite us back. We can fill another hour for you on that one.
Absolutely. Well, and let's dive in. We got a 1 8-minute segment left coming up here, folks. If you want to be on the show, send me an email, info@insideanalysis.com. That does come straight to me. So we want to know what you want to know. We're doing the ed right now for next year. We got podcast bonus segment coming up with these gents next. We'll be right back. You're listening to Inside Analysis. All right, folks, time for the podcast bonus segment here on a fantastic show, Life in the Fast Lane of SDVs. We've got Florian Rohde with us and Michael Franz. And Florian, we wanted to talk about AI and new chips and all that stuff. So go ahead.
Yeah, so I think just to lay the groundwork here, it's important to understand. So AI means there's a large language model, LLM, is getting trained to understand certain things. And right now, what we see is this training happens on a server. So it goes, then the algorithm goes into your car and it has a certain behavior, and it's deterministic. We know what it will do. The next generation will be that there will be training happening within the car. So the car starts to get better. In the first step, that it will hand that back to the server so they can actually test that on the server side and so on. But the next generation, the car will actually get better and learn on itself. And that's going to be super interesting. A little bit of a nightmare from testing point of view, but we were figuring that out right away.
Well, and it'll also learn the user's behavior, right? And kind of figure out, okay, this guy likes to jump off the line and he's stopping too quickly or something like that. You'll get feedback like that. And then Michael, you wanted to talk about the chips as well, because this is the part
Yeah,
that blows my mind. Go ahead.
Yeah, I think what's important is to look at the investments that the chip manufacturers are making right now into the AI chipset, so beyond high performance compute and as you said, as we know today, and that at today's technology has been the limitation in terms of what we could achieve with AI technology. So, give you two quick reference points. One is today you can get vehicles that you can speak to the vehicle under voice technology and ask it about the handbook that you used to get, the owner's manual that used to be in the glove box. They can pretty much put that on an AI chip, and you can speak to the car, and the car can tell you how to operate the radio and all the rest of it, right?
That's crazy.
That's like a chatbot on a website, right? Literally, that's what it is. What Florian is talking about is agent based, where the application or the agent literally starts to train the AI. Train the middleware and the operating system to actually do things. So if we can set up the guardrails for things like autonomous drive, then the vehicle will actually start to learn how to drive by itself, using the inputs from the radars and the sensors, and just operate within the guardrails. So it says when it's a 60 mile zone, don't go over 60 miles per hour, etc., etc. If you are in the right lane, you must turn right. Those kind of rules will be in the guardrails, but the vehicle will take the inputs directly from the sensors. It will learn by itself and continue to learn and evolve and share with other vehicles as it starts to move forward. And that's what's coming next.
Well, and I'm guessing that things it can figure out are, when the rotors are going bad, when the brakes are going bad, things of this nature,
Exactly.
maintenance, and then, the warnings adjust accordingly because now, I've learned just from driving that when you let the rotor get too bad, it starts to wobble a little bit as you're braking. And this is the kind of signal that the car can then capture and then say, hey, you need to go to Midas or you need to go get your
Or
car
call your service
serviced.
tech and get it booked in for a service as soon
Right.
as possible, right? And
Right, but
actually
I
outbound
think
that ticket.
I think Eric, it's important to differ between machine learning and the machine learning algorithm detecting something. So when we talk about learning, the machine, the large language model it learns the capability of understanding something. So this is like me teaching you French. But then you go out and learn new words in French and to speak in French. That is not machine learning. That's not the learning part. That's just like adding information to the system. So basically, on Mike's example, at one point, his dad probably told him how a squeaky brake sounds like, and that is the basics. But then him listening to more and more and more brakes squeaking, that is then what happens in the car. It's basically just adding information, but it's not learning as such. It's just a verbiage at this point.
Yeah. Well, and I'm guessing too that there's tremendous value in predictive maintenance, right? So in a
Yes.
particular model, you see there are these recalls that come in. Well, if you can head that off at the pass, you're going to be much better off. It's going to say, hey, you need to replace this bushing or do this or something else. Otherwise, this part's going to go bad. That's where you're saving really serious amounts of money on work that doesn't have to be done, right?
I read once, I don't know the exact numbers, but a car that breaks down on the freeway and needs to be towed into service is about 20 times more expensive of an incident than a car that is serviced with predictive maintenance.
Right.
Yeah, and it comes to two things, right? OEMs, manufacturers, want to lower their warranty obligation cost, right? I mean, a percentage of every vehicle is put aside to cover things that have to that failure under warranty, right? That's what they have to do. The less a vehicle can be produced and put on the road without a warranty failure, the better for the OEMs from a quality perspective, a brand reputation, and a cost perspective. And for the customer on the road is the most important thing, right? No one wants to be broken. It's not fun to get broken down in the middle of nowhere on a vehicle, on a Sunday afternoon.
It's not fun to be broken down in the middle of the Las Vegas Strip either. So it doesn't
exactly.
where you break
It's
down.
embarrassing. It's embarrassing to be broken down on the Vegas Strip.
That's right.
So Eric, yeah, it's twofold, right? It's a client experience thing. It's also a financial thing, right?
Yes,
I mean, right now we've got Toyota replacing I don't know how many engines on their Tundras and whatever. That's a serious number, right?
Yeah.
And if modern technology and software can start helping improve that side of things at the manufacturing, it'll prevent the warranty issues, the quality goes up, and therefore you start to see the benefit to the customer as well.
I love that.
And brand reputation. I just want to make
absolutely.
You mentioned that already, Mike, but this is actually one of the most important things. People understand, they feel quality, right? And if they feel their car is not breaking down as much as another one, they will buy the same brand again. And so in the end,
they tell their friends.
Yes, exactly. So that's like a marketing that's really hard to put a number on, but it is very valuable.
Yeah, I love that. Feel quality. That's good stuff, man. I'm a car guy. I've got a 2001 Mazda Miata, the 6-speed manual, which is
good one.
Wheels. Yeah,
it's a dream of a car, man. I love it. I love the feeling of it. I love just like I'm a gas guy, and I'm not gonna lie. I like to hit the gas and hear the engine rumble. Like, yes,
right.
Well, I built a replica of a 1965 Shelby Cobra, so I'm with you. But I also have an electric car as a daily driver because I strongly believe the right powertrain for the right purpose.
Yeah, that's right. That's exactly right. Well, this has been absolutely fascinating. Look these gentlemen up online, folks. Michael Franz, it's Frans, the last name, on LinkedIn, and Florian Rohde. These gentlemen are car aficionados. They're experts, and they're helping us get to the next generation of a good quality drive that's safe, that's fun. And I love that line. What did you say? You feel quality.
Feel quality.
Right? You feel quality. I like that. Well, send me an email if you want to be in the show, info@insideanalysis.com. We'll talk to you next time. You've been listening to Inside Analysis.